See this problem. A magnetic field of 100 Gauss is required, which is uniform in a region of linear dimension about 10 centimeters and area of cross section about 10 to the power of minus 3 meter square. The maximum current carrying capacity of a given coil of wire is 15 amperes and the number of turns per unit length that can be wound round a core is at most 1000 turns per meter. Suggest some appropriate design particulars of a solenoid for the required purpose. Assume the core is not ferromagnetic. Our motive is we have a non-ferromagnetic material as a core for a solenoid. This is a solenoid, so whose core is a non-ferromagnetic, and this solenoid has some length and has some turns n number of turns, and there is a uniform field should pass through this solenoid. Assume it to be as B, and it has some area of cross section A, and some current is flowing, that is I. So in this problem we need to find out the design of this solenoid such that it will give a constant magnetic field B whose value is 100 Gauss. So we need to design number of turns per unit length, and we need to design what is the current that we can send into that copper wire such that we will get the required magnetic field. So like that we need to give a design to get the appropriate field. So now I want to investigate the problem. So we need to produce a magnetic field B is equal to 100 Gauss or 100 into 10 to the power of minus 4 Tesla, and the maximum current that can be passed through this copper wire can be taken as I is equal to 15 amperes, and the maximum number of turns that can wound round that core can be N by L is equal to 1000 turns per meter. So you can wound these many turns around that core, and you have area A is equal to 10 to the power of minus 3 meter square. Now I want to resolve the problem. First of all, there is a standard design like that the length of the solenoid should very greater than the diameter of the solenoid. Then only you will get an ideal uniform magnetic field under that solenoid. This is the first condition, so we should follow this. And after that, the magnetic field in a solenoid can be written as mu naught into N by L into I. So here magnetic field depends upon the turns per unit length and the current passing through that coil. Now I want to find the current that can be able to pass through this coil with the given number of turns. So we need to maintain 100 Gauss or 100 into 10 to the power of minus 4 Tesla field, which should be maintained with mu naught into 1000 turns per meter into the current I. If you maintain 1000 turns per meter for the coil to get the required field, what should be the current that can be passed through the coil? So I is equal to 100 into 10 to the power of minus 4 divided by 4 pi into 10 to the power of minus 7 into 1000. 2 zeros cancel. 10 to the power of minus 4, 10 to the power of minus 3 you will get under 0, and you will get minus 2 here. You will get 100 divided by 4 pi, which is equal to 25 divided by 3.14, which is nearly 7.9 or nearly 8 amperes. So if we send an 8 ampere current through the coil which is having 1000 turns per meter, then you will get the required magnetic field, that is 100 Gauss. So here one main problem is there, like the cost of the copper is more when compared to the current that you are sending inside that coil. So here you are using 1000 coils per unit length, so cost is more, and you need to give such a design which will be designed at low cost. So for that we need to consider the formula again. B is equal to mu naught into N by L into I. Mu naught is constant, and the field that required we can kept it as a constant. So N by L is depends on current as some constant K by I. So N by L is inversely proportional to current passing through it. So if you increase the current, we can decrease the turns. So come to the required thing. Now I want to take N1 by L1, which is proportional to 1 by I1, and N2 by L2, which is proportional to 1 by I2. If you take the ratio of these two proportions, N1 by L1 divided by N2 by L2 is equal to I2 by I1. So that implies N1 by L1 is 1000 turns divided by N2 by L2, which should be equal to the maximum current that we can send through the coil is 15 amperes, and with the 1000 turns we can send 8 amperes. So N2 by L2 is equal to 8000 by 15. So with this you will get 533. So using 530 turns and sending 15 amperes, you can get the required magnetic field. So here half of the, so the cost decreases to half. Earlier you have 1000 turns, and now you have nearly 533 turns. That means your cost of purchasing the coil, so it reduces it to half. So this is the best design for that solenoid to get the required field.